Today we are going to move into generalized logarithms. So today we're talking about logs of base A. That means any base we want, not just base 10 like we did yesterday. So yesterday was the common log, base 10. Today we're talking any base we want. Notice that I started these notes with the exact same statement. Anything in math that can be done can be undone. If we can raise any kind of base, 2, 3, whatever, e, pi, if I'm being mean, if we can raise a base to an unknown exponent, there must be an algebraic way of solving for that unknown exponent. That's what logarithms do. That's what we discussed yesterday. Now, yesterday I had the exact same statement here with f of x and f inverse of x, but the difference was the base was 10. It doesn't have to be 10. It can be any base I want. If f of x is a raised to the x, then the inverse of that function is log base a of x. I would like to point out that here a is the exponential base, here a is the logarithmic base. The nice thing is they'll always be the same if they're inverses. So what cancels exponential base 3? Log base 3. What cancels exponential base 5? Log base 5. How about this? What cancels log base 6? Exponential base 6. They are inverse operations. As long as the bases match, they will cancel each other. That's the purpose of a logarithm. If b is equal to a to the x, and of course your exponential base can't be 1 because you can raise 1 to any power you want, you're just going to get 1 back. And we're still only talking about positive bases because negative bases do bad things depending on whether or not the exponent is even or odd. So if we have a positive exponential base that's not 1 and we say, oh, I'm sorry, not and. So what we do is we say that the log in base a of b, and we can say this statement here. Now, this is what they had you do in Algebra 2. They go like, hey, take this exponential and write it in logarithmic form, or they say, take this logarithmic statement and write it in exponential form. I don't like it. I don't like that trick from Algebra 2. So what I'm going to do real quick is just go over to somewhere generic, and I want to show you what you were doing in Algebra 2 as a trick, but I want to show you why it works. Because I highly doubt that the Algebra 2 teacher explained it this way. In Algebra 2, you would have gotten a statement like this. You go, okay, 2 to the third equals 8. We're not solving for anything. This is just a true statement. It's an exponential statement because it has an exponential base. This is what we would call exponential form. And you might have been told to write the statement in logarithmic form. And you might have even seen some kind of cutesy little trick like this or something, okay? Because the logarithmic statement, the equivalent logarithmic statement is log of this, oh my goodness. Come on, active panel. We've been having a lot of tech issues today. Oh my gosh, it's doing nothing. Is it locked? There, okay. All right, anyway, log of the same base of 8 equals 3. Now these two statements say exactly the same thing. They say exactly the same thing. Logarithm can be thought of saying what power of, and then you say the base. So this statement right here, you could read this as what power of, that's what log says, what power of 2 is 8. That's what log base 2 of 8 says. It says what power of 2 gives me an 8. And clearly the answer is 3 because of this over here, 2 to the third is 8. And you would have been converting back and forth between these two statements in Algebra 2. And it's actually where they start the logarithm chapter. And instead of telling you why this is working, they just go, here, write this exponential statement in log form, and then write these log forms in exponential statements. I hate it. Instead, what I would rather do is get you to tell me how, so let's do this again, how would I cancel that exponential base 2? What would you do? What cancels log base or exponential base 2? Log base 2. You see, log base 2 is an operation. It's like saying plus to both sides or square both sides. Log base 2 is an operation. So you are saying log base 2 of both sides. So it's not a trick, it's algebra. And log base 2 will cancel exponential base 2, leaving behind the exponential statement 3 is log base 2 of 8, rather than just trying to memorize a trick. And what about going in the other order? Let's write another true statement, only this one will be logarithmic. Log base, and don't worry, this will be a true statement. Log base, I just did 2, right? Let's do 3 this time. Log base 3 of 1/3 equals -1. This is a true statement. You're not solving for anything. Because it says, what power of 3 would give me a 1/3? The answer is a negative power, a -1. Okay, but you don't have to worry about that. This is a log statement. I want its equivalent exponential statement. What that means is I shouldn't see a logarithm. So I would ask you, what cancels log base 3? Exponential base 3. So what you would do to get the equivalent exponential format is you would, quote unquote, because this is not good math the way I'm writing it, but you would exponential base 3 both sides. What you're doing when you draw those red 3s on there is you're saying these two sides of the equal sign, they were actually exponents. They were exponents of some things that had the same base, and that's why I was allowed to set those exponents equal to each other. And exponential base 3 and log base 3 are inverses of one another, so they cancel out. And you're left with the true exponential statement, 3 to the -1 equals 1/3. So we've seen now why we're able to write exponentials in logarithmic format and why we're able to write logarithms in exponential formats instead of just trying to memorize a trick with some arrows and trying to remember where did the base go, answer and exponent switch places. No. Memorizing is awful. Understanding is key. Memorizing log stuff will only make sure that you can get answers this year. Understanding log stuff will make sure you can get answers forever. Right now I'm teaching a man to fish, okay? Or woman. So what do we have going on down here? These two bold statements, they're just showing you that log base A and exponential base A cancel each other in either order. That's all that says. You don't need to cross them out, but it's saying, hey, look, log base A cancels exponential base A, and exponential base A cancels log base A. That's all it's telling you. So it's showing you in letter format what I just did with numbers. Basically, as long as the bases match, a logarithm and an exponential cancel each other out. That's what they do. So why are these things so difficult for students to understand? I'll tell you why. Because log doesn't look like a symbol, does it? But it is. It's a symbol. It's like a plus sign or a square root bar. It's a symbol. It says, write an equivalent exponential equation for log base 10 of 1,000 equals 3. And then rather than just writing the answer, I'm going to do the algebra that gets us there. If this was an IB question and it just says write down the equivalent statement, the work that you do doesn't get you any credit. But the work is why it's true. And that's why I'm going to show it. I have log base 10 of 1,000 equals 3, and this is definitely a true statement because it says, what power of 10 would give me this 1,000? Well, the answer is 3. 10 to the third is 1,000. In fact, I just said the answer. 10 to the third is 1,000. But how would we have done that without just strictly memorizing? Well, I would ask you, if it says in exponential format, I'm clearly trying, what is happening right now? Ghosts of student past. They have no batteries, but absolutely you can borrow a calculator. Yeah, no, you just pull harder. There you go. Anyway, that's all you needed? All righty. Deuces. I am trying to write an exponential statement, which means I should not have any logarithms. I need to cancel log base 10. Class, what cancels log base 10? Oh, exponential base 10. Cool. So I'm going to use an exponential base 10 on both sides, and I'm going to allow these two inverses to cancel one another, leaving me with the true exponential statement, 10 to the third is 1,000. This is why changing formats works. Shortcuts are not a good thing. Tricks are not a good thing unless you understand. Why did that shortcut work? Why did that trick work? Otherwise, it's just magic, right? Because if we all knew how the magician's tricks work, we would not be impressed because it's not magic anymore. This is not magic, it's algebra. B, we are going to write an equivalent logarithmic statement, so go in the other direction, from this exponential statement. 3 to the 4th is 81. So clearly, if I'm trying to write a logarithmic statement, I need to use a log. That means I should not have any exponentials. Oh, I need to cancel exponential base 3. How do I cancel exponential base 3, class? Log base 3. I'll show one more step of work. I'm going to use log base 3 of both sides. Whatever you do to one side of an equation, you must do to the other. That rule never changes in algebra, and yes, logarithms are algebra. Now log base 3 gets to do its job and cancel exponential base 3, and you're left with the log statement. Log base 3 of 81 equals 4. I'll say it again. They are not magic. They are not mysterious. They're strange looking because they don't look like a symbol, but they are. I will show you my symbol after this lesson. So as soon as I'm finished teaching this lesson, I'm going to show you the symbol that I think if we used to teach logarithms instead of even using the word log, every student would just inherently understand what they were doing. Yeah, I'm going to be honest with you, I've never had a student say to me, I would much rather use the log symbol than the symbol that you drew. And every time I show it, I always have somebody go, can I use it? And I go, no, you can't. It's not real. You can't use it, unfortunately. All right.
Who decided, like, hey, this is what we're using?
Yeah, I don't, you know what happens? It's convention. It just ends up being what was the most convenient way to do things for the most amount of people, and then they all just go, okay, that's the convention. So we have log base 2 of 16. What we have here are 4 logarithmic statements, and what we're trying to do is evaluate them by hand. We're trying to figure out what they equal without a calculator. And these are actually pretty easy ones. I give my Algebra 2 students much harder ones when I teach them logarithms. So the way we're going to do this, you ready for this, is rather than just seeing the answer, or in Algebra 2, you probably would have just written the answer and said why that answer was true verbally, but you would have had no math on your paper. It just would have been a statement and an answer. How do you learn that way? I don't know. That's why everybody hates logarithms so much. And I go, fine. Here's what I would like you to do. I'm telling you, you're going to tell me this thing's value in a moment, correct? Right now, you don't know that value. Let's say you don't know that value right now. In math, what do we typically use for values we don't know? Okay, then why don't we just set them all equal to x? We'll start there. Because now I've created an equation which would allow me to use operations on both sides. Let me be really clear here. This is a lot more work than you would need to do for questions like this. I'm going to show you why in just a moment, but I want you to see how I teach it to the Algebra 2 students first, and then I'm going to show you the much faster way of doing it. It's not a shortcut, it's just a much faster way of doing it. In Algebra 2, I go, hey guys, let's set this thing equal to x. Why? Well, because last unit, we were all pretty darn good at solving exponential equations by hand, weren't we? The no calculator part of the test went very, very well for that one question. You guys were good at that. So instead of trying to solve a log equation, why don't we solve an exponential equation? That means I need to cancel log base 2. In class, how would I cancel log base 2? Exponential base 2 sounds good, so I would just exponential base 2 both sides. Guess what? You do not have a log equation any longer. Now instead, what you have is 2 to the x equals 16. And if you think about last unit, what I did was I said, hey guys, if the exponential bases are equal, then you can just set the exponents equal to each other and you go, is 16 a number that is base 2? Of course it is. It's 2 to the 4th power. So what we have here is 2 to the x equals 2 to the 4. And since the bases match, you just set the exponents equal to each other.
Wow.
In unit 3, when I said when the bases match, you just set the exponents equal to each other and you'll be fine, I said, but by the way, that kind of breaks math rules. There must have been an algebraic process that allowed you to do that. The algebraic process was you canceled the exponential bases on both sides using log base 2, and it left behind the exponents x and 4. So this logarithm has a value of 4. I don't want you to work that hard ever again. Please don't do that. In fact, for these last ones, I'll keep the x equals because I already wrote it, but I'm not going to be turning my logarithms into exponentials unless I have to. I don't want to do that unless I have to, okay? So when would I have to? Maybe if it was a complex one. Not, and I don't mean imaginary. I mean like maybe if it was a difficult question, okay? So how would you have done this the quick and painless way? Because this is kind of painful. Log base 2 of 16. So this is equivalent, but much, much easier. Yeah. Let me ask you a question. What does log base 2 cancel? Exponential base 2. This log base 2 wants to do its job. But it can only do its job on exponential base 2. So you look at the argument of the logarithm. That means the number you're trying to take the log of. The inside, when you have parentheses around it, it's called the argument. The argument is 16. Is 16 a base 2 number? Well, of course it is. It's 2 to the 4th. So instead of saying log base 2 is 16, tell you what I'm going to do. I'm going to allow log base 2 to do its job by changing 16 to a base 2 number. And now log base 2 can do its job. X equals 4. If you were taught logarithms this way in Algebra 2, none of you would have bad memories of them, in my opinion. It's pretty easy, isn't it? It's not magic. I hate how logs are taught. I'm going to tell you the reason why most math teachers don't show them this way is because most math teachers don't understand them this way. It is not any offense to their intelligence. It's just that most people don't like logs and they do their best to avoid them and they grit their teeth and bear it when they have to do it. I love logarithms and I go out of my way to try to find difficult log problems to challenge my skills. They're not difficult as long as you understand what they are. So I would like to use the short method for for evaluating each one of these numbers. You have a question for me?
Why were you able to just do log base 2 on the left side?
Well, I didn't actually do log base 2 on the left. Log base 2 already existed there. I was just letting it do its job.
Oh, yeah.
Yeah, so if I said like, hey, what's the square root of 9? You're not doing anything to both sides. You're just allowing the symbol to do its job. And log base 2 is a symbol. A weird one, but it is a symbol. So right here, you know that log base 5 has a job. Log base 5's job is cancel what? What did exponential base 5? That means in order for it to be able to do its job, when I say do its job, I mean like square root bar, square root of 2. It can't do its job on a 2 very well, so you just have to say square root 2. Well, log's the same way. What's log base 2 of 3? Yeah, it's log base 2 of 3. That's the best way to say it. Because if you say it any other way, you end up with an irrational number. But log base 5 can do its job if its argument is base 5. And you know what? 0.2 is base 5. Because 0.2 as a fraction is 1/5.
Wow.
And I go, okay, can 1/5 be written as 5 to some power? Of course it can. What power? -1. So this is actually log base 5 of 5 to the -1. Now log base 5 can do its job. X equals -1. That means that that logarithm has a value of -1. And what would be great is if you could start looking at these things. I challenge you to get so good at them that you could just look at this next one and you could see that the answer is 2/5. And that you look at the last one and you could see that the answer is -1/2. Like, I challenge you to get there. And eventually, I think you can. But let's find those answers. How'd I know those so quickly? Well, we're going to go back to the common log for a moment, log base 10. Log base 10 has a job. Its job is cancel exponential base 10. And just to really drive home the point, I'm not even going to write base 10. I'm just going to write log, the common log. So, you know what? No, I'll write it. I'll just write it because I think it's better for education. I know that this argument needs to be written as a power of 10. Square root, fifth root bar is what power? What the fifth root, that is an exponent. What power is it? That's the 1/5 power. And 100? Well, 100 is a power of 10. What power of 10 is it? It's the second power. So I'm going to show a lot more work than you need to, but just so we can get there together. I'm clearly running out of space. I'll have to clear. And just to drive home old skills as well, I have a power raised to a power right here. When you raise a power to power, what do you do with the exponents? Multiply. So I have 2 times 1/5, which is just 2/5. And at this point, log base 10 can do its job and leave the answer of a value of 2/5. So how did I do it so quickly? I noticed that the 100 was 10 to the second right off the bat. And I said, oh, 10 and the fifth power, or the 1/5 root. So 2/5, like that. And it would be great if you could start getting there. If you can't, that's fine. As long as you understand how I'm getting these answers, and you can do the same. I need space, necesito más espacio, so I'm going to try this one more time. What is happening to the board right now? There we go, lock. So I can make some stuff smaller because I needed space. Now I have space. My x's don't line up anymore, but hey. Yeah, the board is fun to use. I've practiced a lot. Okay, I'm gonna re-put the x up here, even though it's not necessary, but let's just go ahead and do it. Cool. We know log base 2's job. Log base 2's job is to cancel exponential base 2. I'm gonna take this one step at a time. Even though you don't have to, take it one step at a time. First things first, my exponential base is not a fraction. So why would I want my argument written as a fraction? That kind of makes things difficult. So how do I turn things that are fractions to not fractions, other than using decimals? You use a negative, sorry, I just got these lips. You use a negative exponent. So square root 2 raised to the -1. Cool. Oh, that's right. I need an exponential base 2 statement. Square root bar is what exponent? 1/2. So log base 2 of 2 to the 1/2 to the -1, again showing a lot more work than you need to, but there it is. And just like the last question, when you raise a power to a power, you multiply those exponents. So you're left with log base 2 of 2 to the -1/2 equals our unknown value, and our log base 2 gets to do its job, leaving me with the answer of -1/2. So how did I see the answer so quickly? Well, first one was a trick. I saw that my base wasn't a fraction, but my argument was. When they're not both fractions or not both whole numbers, your answer is negative instantly because you must have flipped something over. And then I just saw the square root and said, oh, 1/2. So I saw it was upside down, negative, saw the square root bar, 1/2, answer, that fast. Zach, yay or nay?
Never mind.
Good?
Yeah, I'm looking at it closely. My question is
Okay.
not needed.
All right. Well, hey, if it comes up that it is needed, you just let me know. I know logarithms are not everybody's strong suit. If you would like to ask me anything, please do. We're not ready for the symbol yet. There's a back to the notes. We're not ready yet. Okay. Then I will flip. Can I go to the next? You have a question? Okay. So then let's go to the back. And these are the last two things we're going to do, I believe, right? Like that's it for the notes? Great. We are going to solve these two logarithmic equations. And these are rather simple logarithmic equations, to be honest with you. Don't worry. We'll do the harder ones soon. You see how I said that? I just love quadratic logarithms. They're just fantastic, okay? Yeah, they are really cool. I also like doing trigonometric logarithms. That's a lot of fun. Or infinite series logarithms. Those are fun too. Okay, I love logarithms. So here we go. We are trying to solve a logarithmic equation. There's more than one way to do this. There's more than one way. But I would like you to see that this first example, the base is unknown. The logarithmic base is unknown. So, what do? You don't go back to sleep. That's for quitters. No. What you do, I think the easiest way to attack this question for most people is you just go, maybe it would be easier if it was in an exponential form and not logarithmic form. Maybe that would be easier. Maybe. I'm not Victor, but yes. Here's what we're going to do. We are going to exponential base both sides. So we need to cancel the log base x with an exponential base x. Yep. So we now get, and can I please switch my variables to the left side? So it says x to the -3/2 equals 27. Well, I did it anyway. Like how I asked as I did it, but there it is. Okay. Now. How do we normally cancel exponents? With radicals of some sort, correct? But what if I said to you that when you cancel a square, let's just say, you say you use a square root. And I go, well, isn't a square root technically a 1/2 power? So when you had x to the second, how did you cancel the power of 2? It's reciprocal. Because when you raise a power to a power, you multiply. That's why the square root cancels the square, because they're reciprocals. That's why that works. So what I'm going to do is raise both sides to the reciprocal power. Because when you when you raise a power to a power, you multiply. And you see, when you multiply reciprocals, you get a 1. So that gives me x raised to the +6/6, which is just x raised to the 1. But on this side, I have 27 to an exponent, and we can evaluate this by hand. Showing lots of work. To be honest with you, the next one's easier than this one. Well, the bottom of the fraction is a 3. What does that tell you? There's a cube root. Someone said it. That means there's a cube root. There is your 1/3 power. And then I'll deal with the -2 power in a moment. We'll deal with that in a moment. What is the cube root of 27? 3. Okay. So right now I have 3 raised to the -2. And negative exponents, they make things move across their own fraction bar, right? So this would actually say x equals 1/3 squared, which is 1/9. So that unknown logarithmic base was 1/9. I bet you I could name a curve that you have never, ever seen graphed. Log base x of 2. Now, you saw log base 2 of x in Algebra 2, but bet money you've never seen log base x of 2, where the base is the variable that changes. Let me tell you, it's a really interesting thing. There's no way. There's no way. I've searched Google. I've never even found it on Google. Don't do it now. We're working. Now, that doesn't mean that you can't go to graphing programs and have them graph it, but I've never found any. Yeah, I've never found any questions regarding it online. Now this one is easy. This one's much easier than the last one. We need to cancel that logarithm. That logarithm is log base 4. What cancels log base 4? Exponential base 4. We don't want to say 4 because that's dangerous. Some people might multiply both sides by 4. It's exponential base 4. And that's why I make them so big and obnoxious, because I want you to realize it's a base. And the crap that you had, that's exponents. Well, this is gone. So I just have the argument left behind, 2x plus 1 equals 4 to the 3 halves. And we can evaluate 4 to the 3 halves easily by hand, because the 2 on the bottom of that fraction represents what? Square root. The 2 on the bottom of the fraction represents the square root. And then the 3 will be evaluated later, because the square root of 4 is just 2. And I think it's pretty obvious what we're going to do from here. 2 to the third is 8. And now it's algebra 1. Subtract 1 and divide by 2. Leave your answer as a fraction. It's better. Yeehaw, logarithms. Gosh, I love logarithms. They're so much fun. Simple now, right? So much better. Now, I would like to show you the symbol that I created that represents a logarithm rather than using a symbol. But instead of writing it and then trying to explain it, instead I'm going to ask you to please pretend you have never even heard of a logarithm. Just for a moment, pretend you've never heard of logarithms, and I'm just going to show you a couple math statements, and you will notice that my symbol intuitively tells you what it does. Watch. Shh. Watch. All you know right now is that it is possible to raise things to powers. That's all you know, and you know that it's possible to cancel exponents. That's all you know right now. So watch, no, pay attention because you forgot what I did. Here we go. Okay, and let's do something that you could have solved using brain power, okay? Some unknown number raised to the, let's just say, second power is the number 9. I know you know the answer, but I don't care, okay? If you were trying to find the answer algebraically, you would have done this. And that root would have had an index of 2. Do we always write the index 2? No, it's never written, but it's just like common log. It's because it's the most common root. We're just being lazy. But it's always there. It's always there. And why does this work on the right side? Well, let me show you why it works. Because the symbol is doing its best to cancel a second power. Oh, luckily, 9 is something raised to the second power, which would allow my symbol to do its job. Correct? Okay, so we're all comfortable with this radical canceling a matching exponent, right? Yeah. Awesome. Unimportant to me that you know the answer. Unimportant. My point is, there must be an algebraic process that gets x alone.
Oh, you wizard.
Allow me to introduce you to the subroot.
Tell us, Makanji.
And I feel like you all intuitively understand what it does. You see, the subroot 2 would only be able to cancel things that are base 2. So 8 must be a number that is base 2, allowing the subroot to do it. Ooh, dang it, I drew it upside. Allowing the subroot to do its job. And the subroot of 2 would cancel exponential base 2. Oh, I wrote that. It's really an upside down square root. Well, doesn't that make sense? Yeah. The root, regular square roots, regular radicals cancel exponents, upside down radicals cancel the thing underneath exponents. Even if you've never seen a logarithm, you intuitively understand what that's doing. But it's not a real math symbol, so you're not allowed to use it. I am so sorry. Yet. The power of yet. Now, if you ever see this done in the future, you remember you saw it here first. Ah, that's the McCutcheon move right there. I like it.